this over here is a Venn diagram. What does it include? It is a sample space. You know, usually we call that big rectangle, we call it a universal set. And inside here we have the elements, the possibilities, the outcomes of what will happen if you roll a die. How many faces does the die have? Six. It is a cube. So you got numbers 1, 2, 3, 4, 5, 6. Okay, so we scatter them inside there. Those are our outcomes, they are our elements. So they circled this 3 and 6. They call it an event E. Okay, what's something common about 3 and 6?
They are multiples of 3.
They are multiples of 3, they are factors of 12. Okay, both was can. Hey, but 1 is also a factor of 12. Right, but they didn't circle 1, right? So maybe it is more accurate in this case to say that they are multiples of 3. Okay, so here we have some definition, random experiment. So when they say random, it is really random. There is no bias. In other words, it is unbiased. And whatever is the result is known as the outcome. So the probability of an outcome is a measure of the chance that it will happen. So what is the chance that you will start pouring with a thunderstorm right now? Very, 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 very low. In fact, close to 0 because it's so sunny right now. Okay? But this is Singapore, we'll never know. Okay, next. Okay, instead of a universal set, in probability, we call it a sample space. It is just a name containing all the different possibilities. So, the probability of something happening, the probability of an event E happening, in this case we call E as multiples of 3. If we call the event multiple of 3, there are 2 elements, there are 3 and 6. So what is the probability of the event happening? It will be 2 cases. The number of outcomes favorable to the event. How many outcomes are there? 2, 3 and 6 only. So there are 2 outcomes over the total number of possible outcomes. How many faces does it have? 6. So what is the probability that I throw a die? I get either 3 or 6. 33.3333%, which is actually 1 over 3, right? So we can call it 1/3. Would you rather say 1/3 or would you rather say 0.3 recurring or would you rather say 0.333? 1/3. Let's use 1/3 because it is accurate. So in probability, we will often see fractions being used as opposed to decimals or percentages, which are also okay. Okay, so here we have the sample space as it is again a set. It contains 1, 2, 3, 4, 5, 6. There are 6 elements. Now this symbol over here, n. N with a bracket. Remember you saw this symbol? During your test that I told you to cancel out? Because it's no longer in syllabus. But this just means the number of elements. Okay? So number of elements inside my sample space S is 6. Because in probability, we need to count the number of outcomes. So instead of writing the number of elements, we just write n with a bracket. You can write it, but you shouldn't have a need for it. Okay, so inside the event, which is multiples of 3, there are 2 elements. They are 3 and 6. So the probability of us getting a multiple of 3 is number of elements, 2, they are favorable, divided by the total number of possibilities, which is 6, and we get 1/3. Okay, I don't think this is any problem to you. Let's take a look at this table over here. This highlighted portion. The probability of an event happening is always between 0 and 1. It can include 0. For example, like I said, the probability of me suddenly growing by maybe 2 meters in the next 1 second is 0. It is impossible for that to happen. And the probability that something can happen at most is 1. So what does it mean by the probability is equal to 1? That is 100%. It is going to happen. We know it is going to happen. What are some things that are really, really certain? Actually, it's really quite tough to really say that something is bound to happen. Your gender? What is the probability that the water Okay, can. What's the probability that the water will evaporate over time? Yeah, okay. 100% lah, you will definitely evaporate, right? Why not? Okay, you get my point lah. Huh? Now, point number two. Point number two, the probability of something that will confirm happen is 1. Point number three, the probability of something that can never happen is 0. And what does this dash over here mean? Right. Okay, what does it mean?
Event that never happened. And everything is
Okay, so in set, chapter, or was it 1 or 2? 1. 2. 1. In chapter 1, we learned about complement, right? Complement of a set means everything is also of a set. So here this means that probability of the complement of the event. Can you recall what is the event in this case?
Yes.
Multiples of 3, right? That means 3 and 6. The probability of the complement, what are the elements inside this complement?
1, 2, 4, 5.
1. No, there's no 0 in the die.
1, 2, 4,
So it's 1, 2, 4 and 5. Those are the elements inside the complement. So the probability of that happening, either 1, 2, 4 or 5, must be 1 minus the probability of the complement. Because it is either you get a multiple of 3 or you don't get a multiple of 3, right? If the probability of multiple of 3 is 1/3, then whatever is not a multiple of 3 will have a probability of 2/3. It's one or the other. They must add up to 100%. So next part, how are we going to simplify our calculations? Because it can get quite complicated. Now, if the random experiment involves 2 processes, early on we were talking about 1 process only. You throw a die, that is 1 process. 1 process of throwing a die, you get 6 outcomes. You flip a coin, that is 1 process. You get 2 outcomes. But if there are 2 processes, what do we do? For example, example number 1, an unbiased coin is tossed. That means when you toss a coin, you either get 50% chance of head, 50% chance of tails. That is 1 process. And then the other process is to select a letter from the word amend. A, M, E, N, D. 5 letters. So there are 2 processes over here. How are we going to combine them together? We're going to use this thing called a possibility diagram. I will explain how it works. This possibility diagram will show us every possible scenario. Do you agree that we could get a head and the letter A? We could also get a head and the letter M, right? Head and E, head and N, head and D. And tails for everything else, right? These are all possible. So, we have to illustrate everything in our possibility diagram. And we will use this format. Okay, the earlier format, the one with the crosses. All this, we don't really use this. But generally, what this means is that, well, you've got a coin, it could be a tail, it could be a head. They have the letters. These crosses, they all represent the possibilities. And for example, if I ask you what does this point over here represent? It means you get a head for the coin, and you choose the letter M. Okay, but you need to keep referring to the axis, vertical and horizontal axis.
So,
Yes?
pure chem got one question like this.
Huh? What?
Pure chem got one
What is pure chem?
I mean, pure chem.
A pure chem. Oh, okay. Oh, I forgot. Probability of getting a head as well as the letter M. Head and the letter M. There is only one possibility. So it is 1 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The probability is 1 over 10. Simple enough. All of them are equally likely. So your turn. Try it now. Question 1. Try 1. Use a table like this. And this is how I want you to present it. Can I have goal 1 and goal 1 at the same time? Cannot. So this box over here has to be left blank. It is not possible. Get it? Okay, now move on to the second one. Can I have the first draw, I draw the gold coin number 2 And then after that, in the second draw, I draw gold coin number 1. Is this possible? Yes, it is. So here I draw silver coin and I draw gold coin number 1. The next possibility, the first draw, I draw gold coin number 1. Can I draw gold coin number 2 this time? Yes, because they are separate gold coins. So this is G number 2. Can I have gold coin 2 and gold coin 2 at the same time? Cannot. Next one, silver and gold 2. Fill in all the blanks. Gold 1, silver. Here we have gold 2 and silver. And I cannot have silver, silver. Okay, the possibility diagram? Anybody needs help? Then let's do the question. Find the probability of getting 1 gold coin. Do they care which gold coin it is? No, they don't care. Either gold 1 or gold 2, don't care. And 1 silver coin. Highlight. Or you can circle. 1 gold, 1 silver. 1, 2, 3, 4. So what is the answer? Probability 1 gold, 1 silver is equal to 4 over 1, 2, 3, 4, 5, 6. 6. So answer is 2 over 3. You have to be comfortable with writing your statements this way. Probability of getting 1 gold, 1 silver. Okay? But this obviously doesn't mean P times 1 gold, 1 silver. So 2 over 3. Now your turn, try number 3. I'm sure you can fill out the table yourself. I don't want to waste time. I want to go into part B. Hence, find the probability that both eggs taken are good. Both are good. Is it 10? So I've got a... I know it is without replacement, right? Okay, so there's nothing here. Nothing, nothing. Both of them are good, which means... 6 out of 12, which is half. So probability both good is 6 over 12, which is 1 over 2. Okay, you fill in your possibility diagram yourself, huh?
So I put P bracket, put in, comma, put in bracket.
Can. Okay. Sometimes it is not as simple as 2 processors. Sometimes you have 3 processors. Can you imagine, if you have to draw a third time for the 8th question? How, Okay, class. Point tag. Let's exercise our brain a bit. We are doing this, drawing 2 eggs. One at a time without replacement. The possibility is, diagram looks like this. What if I include a third process to draw a third egg? What should it look like? Triangle. How are you going to draw it? How are you going to draw it? Anybody? Huh? 3D? 3D? Like this? Yes, Yeah, it's like this, right? No, I mean, yeah, literally it's right. You get a 3D, you get a cuboid like this. But can you imagine the difficulty you will have trying to draw whatever is in the middle over there? In the middle, how are you gonna like pull all the cubes out and look at what's in the middle? So we have this thing called the tree diagram. The tree diagram is for more than 2 processors. You have 3 or more. So for example, if you throw a coin, we have 2 possibilities. Head and tail. Class. Watch. This is the first time we are going to be using the tree diagram. Am I right? Have you used it before? I don't think so. But you might have seen a variation. Okay, so let me introduce this to you. It is for 3 processors or more. We always start from 1 point. Is there a header to this point? Is that name? No, there isn't. You have 2 options. You get either a head or a tail. And we give it a header. We call it the first coin. The first coin, you can get either a head or a tail. What is the probability of getting a head? Half. All of you write down half. Write down the half over here. So, the probability of a tail is also half. Okay, so that is our first process. Now, if I end up with a head, then I toss my second coin. What are the possibilities of my second coin? Again, head, tail. That is another half, and another half. Now, if my first coin is a tail, what are the two possibilities for my second coin? Still a head and a tail. Still get another half, and another half. This is so far two processes. For two processes, in this case, how many outcomes do I have? Head, 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 tail. Tail, head, tail, tail. I have 4 outcomes. But if I have a third coin, it is going to double again. Okay? 2 power 0, 2 power 1, 2 power 2, 2 power 3. Okay? So here we have another half. So put in all your halves. It is not a waste of time because we have to include this for our exam. So put all the halves over there. And finally on the right hand side we write down the outcome. Outcome is you follow the branch. Head, head, head. So put on head, head, head with a comma. Include the comma. Can you imagine if there are numbers for dice? So you can't be writing 123, right? Well, write 1, 2, 3. So put in all your commas over here. Put them in. Okay, so how many possible outcomes are there for this throwing of 3 coins?
8.
How many outcomes are there? There are 8 outcomes. There are 8 outcomes over here. Out of which, how many head, head, head are there? Okay. How many tail, tail, tail are there? How many head? How many combinations, or rather, how many possibilities of 2 heads and 1 tails are there? 2 head, 1 tail. Count. 2 head, 1 tail. 2 head, 1 tail. 2 head, 1 tail. 3 only, is it? 1, 2, 3. 3 of them. 3 out of 8. Okay. What is the probability of at least 1 head? Is it half? At least 1 head. Okay, think about the question. Some of you can get it really fast. Then the other students must be thinking, hey, how come you can count so quickly? What is the probability of at least 1 head? Can we do it without counting? How? So at least 1 tail. Did I say 1 tail or 1 head? Wait. Huh? Okay. What is the probability of at least 1 tail? Means 1 minus probability of at least 1 tail. Okay, common phrase that we will see. This is the same as probability of, this is the same as 1 minus probability of no tail. Hey, wait, at least 1 tail means, all head. Agree with this? At least probability of at least 1 head means 1 minus probability of all. What am I saying? Probability at least 1 tail is the same as 1 minus probability you get all heads. Okay? So this is an example of using complement. It is either you get at least 1 tail or you get all head. No other way around it. So this is 1 minus 1 over 8, which is 7 over 8. Don't need to count. But you want to count again? Okay. Next one. Try it 4. Please try it now.